Hi, welcome to my channel Smart Easy. Today I'll explain design of FIR filter using Windows. Let us have the procedure first. First, we have to choose the desired frequency response of the filter, which is designated as HD of omega. Next, take the inverse Fourier transform of HD of omega in order to get an infinite impulse response of the filter HD of n. So remember, this HD of n is a infinite impulse response. In order to convert this infinite impulse response to a finite impulse response, that is h of n, we have to multiply h of n by choosing a proper window sequence w of n. So before we proceed to that, the first step is we have to choose a window sequence w of n. So here this window sequence, it may be a rectangular window, Hamming window, or a Hanning window, or Blackman window, or Kaiser window. Whatever it may be, that we have to choose. After choosing this window sequence, multiply this W of n with HD of n in order to get a finite impulse response H of n. After getting a finite impulse response h of n, apply the z transform of h of n to get the desired digital filter transfer function h of z. So today I'll explain one simple problem in a easy way by choosing a rectangular window method. Before reading the actual statement of the problem, let us see how do we define the rectangular window sequence. Here we call it as a window function or weighing function. For an n-point rectangular window is given by here WR of n, which is equal to 1 over this interval minus n minus 1 by 2 to plus n minus 1 by 2, otherwise 0. Another way of representation is WR of n, which is equal to 1 from 0 to n minus 1, 0 otherwise. Here the problem: design a linear phase FIR low pass filter using rectangular window by taking 7 samples of window sequence and with a cutoff frequency omega c equal to 0.2 pi radians per sample. Here this is the problem. Try to understand. Here we have to design low pass filter. Therefore our desired filter is low pass filter, and we have to use the rectangular window sequence to design this low pass filter, and the number of samples is given as 7, that is capital N equal to 7, and the cutoff frequency omega c is 0.2 pi radians per sample. Okay, before we start our problem, I am requesting you all, let us keep your Cal C particularly in radians mode. Okay, right, let us choose symmetry impulse response with a symmetry condition h of n minus 1 minus n, which is equal to h of n, and here the desired ideal frequency response hd of e power j omega or hd of omega, whatever it may be, that for FIR low pass filter. This you have to remember, and you have to write this particular range very carefully. hd of e power j omega, which is called as a desired filter frequency response, which is equal to e power j omega alpha e power minus j omega alpha over the period minus omega c to plus omega c, otherwise 0. So as per our sequence, the next step is immediately we have to take the inverse Fourier transform of this hd of omega in order to get infinite impulse response of the filter hd of n. So by definition, the inverse Fourier transform hd of n, which is equal to 1 by 2 pi over the integration minus by 2 pi. This is the sequence hd of e power j omega into e power j omega n into d omega. So as all of you know, over this period, see here, this is the desired response of the filter hd of e power j omega equal to e power j omega, that I am going to be substitute here over the period minus omega c to plus omega c, e power minus j omega alpha into e power j omega n into d omega. So 1 by 2 pi over the integration here exponent of I'll be taking j omega is common and n minus alpha into d omega. So 1 by 2 pi integral of e power x, which is equal to e power j omega into n minus alpha by j n minus alpha, and we have to substitute the limits from minus omega c to plus omega c. After substituting this limit, which is nothing but 1 by 2 pi e power j omega c n minus alpha minus of e power minus j omega c into n minus alpha divided by j into n minus alpha. So here we'll continue, which is equal to 1 by pi n minus alpha. Let us take into this side and make n minus alpha into the side. Why? Because our intention is we want to keep in e power j theta minus e power minus j theta by 2j, so that comfortably we can write sine theta form. So this has to be written as, which is equal to sine of omega c into n minus alpha by pi into n minus alpha. This is a valid equation for all the values of n except n equal to alpha. What happens if you substitute n equal to alpha? It will become 0. So 0 by 0, which is a indeterminate form. So in order to simplify this, we have to apply L'Hospital rule. Why? Because we want to know what is the value of HD of n when n is equal to alpha. So that we have to apply the L'Hospital rule, which is nothing but when n equal to alpha, HD of n, which is limit n minus alpha approaches to 0, this is sine theta by this actual function we have to write. As all of you know, while applying this L'Hospital rule, HD of n 1 by pi limit n minus alpha approaches to 0, sine omega c n minus alpha by n minus alpha. The whole function will become omega c. Why? Because we know the L'Hospital rule. When theta approaches to 0, sine a theta by theta, which is equal to a. So when compare these two equations, in place of a, we have omega c. That is the reason I wrote here as a omega c. And already we have a constant 1 over pi. So HD of n, which is equal to omega c by pi. This is the value of HD of n only when n equal to alpha. Otherwise, this equation is a valid equation for all values of n. Next, the impulse response h of n of FIR filter is obtained by multiplying HD of n by window sequence. I told you in the problem itself, here we have chosen rectangular window. This is the sequence of a rectangular window, WR of n, which is equal to 1 over the limit n equal to 0 to n minus 1, otherwise 0. So we have to multiply this WR of n with HD of n, so that we will be getting a finite impulse response h of n. So before we proceed, so see here, impulse response. This is a finite impulse response. How do we get? Multiply HD of n with the window sequence. So window sequence, which is equal to 1 over the range n equal to 0 to n minus 1. So h of n equal to HD of n for n equal to 0 to n minus 1. So in the problem it has given n equal to 7 and the cutoff frequency is 0.2 pi radians per sample, and alpha has to be computed using the formula n minus 1 by 2, which is 7 minus 1 by 2, which is equal to 3. So we have to calculate the value of h of n for n equal to 0 to n minus 1. So here capital N equal to 7 minus 1. So we have to compute the value of h of n for n equal to 0 to 6. Next, we know that the impulse response h of n satisfies the symmetry condition, that is h of n minus 1 minus n equal to h of n. So that we have to calculate only n equal to 0 to 3. Actually, n has to be computed from 0 to 6, totally 7 samples. So to use this symmetry condition, it is enough to calculate only from n equal to 0 to 3. Let us see here. When n equal to 0, compute the value of h of n, I mean h of 0. Sine omega c n minus alpha by pi into n minus alpha. In place of n, substitute 0, you will be having the sample value. When n equal to 1, this is the value. When n equal to 2, this is the value, and n equal to 3, I told you already, if you substitute directly over here, you will be having 0 by 0 indeterminate form. So apply the L'Hospital rule. Already we computed this value, which is equal to omega c by pi, and we know omega c equal to 0.2 pi by pi, and which is equal to 0.2. So for computing n equal to 4, 5, 6 further sample values, we can use the symmetry condition. H of 4, I mean h of n equal to h of n minus 1 minus n. N minus 1 is 6, 6 minus 4 is h of 2. So h of 4, which is equal to h of 2. So already we computed this h of 2 value. See here, like 0.1871. So similarly, when n equal to 5, h of 5, which is equal to 6 minus 5, h of 1. So h of 5 and h of 1 both are equal. And similarly h of 6, which is equal to h of 0. So the transfer function, I mean the desired filter transfer function h of z of FIR low pass filter is given by taking the z transform of h of n. That is h of z equal to z transform of h of n, which is equal to sigma n equal to 0 to n minus 1, h of n z power minus n. And we know n is varying from 0 to 7 minus 1, that is 6, h of n into z power minus 1. Here is the remaining expansion over here. So h of 0, h of 1 z power minus 1, h of 2 z power minus 2, and has to continue up to h of 6 into z power minus 6. And already you know that due to symmetry condition here, few of the samples are equal, like h of 0 equal to 6. So 0 and 6, let us take common as a h of 0, and 1 and 5 both are the samples have same sample value. So let us take h of 1 as a common, and z power minus 1 plus z power minus 2. Take the h of 2, why? Because these two samples are same value, and h of 3 into z power minus 3. So substitute the values of h of 0, h of 1, h of 2, h of 3. So we will be having the complete structure of h of z, which is the desired filter transfer function. Here we got this transfer function for low pass FIR filter. If you want to realize this transfer function, we have to choose suitable structure and has to draw the diagram. Thank you for watching my channel. For more updates, please subscribe my channel. Thank you.